So our guest speaker today is Carlos Oscar Sanchez Orzano. Carlos Oscar is an electrical and computer science engineer, a mathematician with a specialty in statistics, and he holds 2 PhD degrees, one in biomedical engineering and one in pharmacology. He provides expert biostatistical advice for animal studies at the National Center of Biotechnology in Madrid in Spain, where he also serves in the local animal ethics committee. He's also a teacher in our Function B course at the Karolinska Institute. He has over 200 original scientific publications, and in 2019, he published an open access book entitled Statistical Experimental Design for Animal Research, which is the topic that he's going to cover today. So welcome, Carlos Oscar. Thank you very much for joining us today. We are looking very much forward to listening to your talk, and when you are ready, the floor is yours.
Okay, so thank you, Rafael. Thank you for the invitation and all of you for attending. So today, in just 1 hour, I will try to introduce you to experiment design and a little bit of the logic behind. And these are the topics that I will cover: completely randomized design, randomized complete block design. So all these are statistical names you may not be familiar with. And we have a couple of questions before going into the lecture, the talk itself. So Rafael now will send you a link to the first question. So if you can answer. Okay, so this is actually a very interesting result, because experimental design is about identifying sources of variability, and not so much to reduce the number of samples. Both are somehow linked, but they are not exactly the same. But yeah, very often these are the main 2 topics. So reduce or calculation of the sample size, and the other one is how to identify which are the sources of variability that is the topic of experiment design. Okay, so now let's go for the second question. Yeah, these results are also interesting. The 2 most common ones are the ones that are more widely used, which yeah, it is a kind of redundancy. But yeah, these completely randomized designs are the most basic ones, and people that are a bit more advanced, they put blocks in. Okay, so yeah, so let's see all these designs. Okay, so we will start with completely randomized design. That is the most widely used, and then we will refine it into blocks. Okay, so for doing that, yeah. So what we'll try to see today is to learn a tool that is much more powerful than the 2 independent groups student test, which is fine. It solves a lot of problems, but it is not the only tool. And the other tools will give you a lot of insight into your problem. So let's start with the completely randomized design. So let's say that you're testing a new drug and you have some given dose, and you want to see, I'm putting the example with people rather than with animals, but it is the same. So you want to see if this new drug lowers the blood pressure of these people. So let's say that all of them have high tension, high blood pressure, and you will use 1,000. So 500 of them will receive a placebo, the other half will receive the drug. And then for every person, you will have a measurement. So you will have you have 2 columns, one for each one of the treatments. And this is person 1 in the first treatment. This is person 2 in the first treatment, person 500 in the first treatment, and the same for the other one. So one is placebo, the other one is the drug. Then you can compute averages of all these treatments. So you compute the average of all the people receiving the placebo, all the people receiving the treatment, and you want to compare those 2 means. And also you can compute the overall mean. So if the drug is not effective, what you would expect is that the 2 means are similar to each other and they are similar to the overall mean. If the drug is doing something, then the placebo and the treatment drug will have different means, and both of them will be different to the overall mean. Okay, so we have to model our acquisition, our data. So what we are saying here, I'm sorry, but statistics is a branch of mathematics, and I don't want to hide all of them, because otherwise everything becomes like a kind of magic. Okay, so what we are saying here is that in treatment J, and for person K within that treatment, we have an overall mean plus something that depends on the treatment that you have received, plus something that depends on that specific person. That is all we need from this equation. Okay, so let's see. Let's say that we have a control, we have a treatment. We think that our treatment is effective. So we would expect to have a situation like this. So we would have some people in the control group. Every point is a person there. And then we can compute the mean of that group. So the mean of that group should be the overall mean plus the effect of being in that control. That if the and that for the treatment, it would be the same. We have a number of people, and the mean of the treatment should be the overall mean plus the effect of being in that treatment. And because the treatment is effective, the mean of the treatment is smaller than the mean of the control. So that means that the overall mean, the mean of all groups together, it is smaller than the mean of the control by itself. And you may notice here that the distance between the control and the overall mean is the same as the control, as the overall mean and the treatment. So one is positive, the other one is negative. So the addition of the two is 0. This is a property of all these ANOVA-like methods. So I'm sure that you have used ANOVA previously. And one of the constraints that ANOVA is putting is this one. Okay, so then let us analyze one single person here and one single person there. And don't be scared about this equation. We will explain it, and it is very easy. So let's say that we have a single person here. We have the first person in the control. So the first person in the control will have a value, and we can decompose this value into different components. The first one is that it will have an overall mean, and on top of this overall mean, it will have the contribution of its own group. So if it is in the control group and the mean of the control group is higher than the overall mean, then this person will be shifted higher simply because it belongs to that group. And then it will have something that is intrinsic to it. So we have some noise or some variation that we cannot explain by being in this group. So the value obtained here, experimentally obtained, will be an overall mean plus something that depends on the group you are plus something that depends on that person. And then if I want to compute the distance from this observation to my control group, what I have is the variation of that person. And if I want to compute the distance between this person and the overall mean, I have both contributions. So I have this red line. So it is the difference between me and my group, and between my group and the overall mean. And the same happens here. So you can go from a person that has been treated. So you can go from that person to the mean of that group, and then from the mean of that group to the overall mean. So that is what is explained here. So here what we are saying is, okay, so what are the total variations? The total variations are the difference between these people, every one of these people, and the overall mean. So we will see some variations. And these variations, part of them can be attributed to the group that you are. So part of them is because you are in the control or the treatment group. And a part of it is because people are different. This is this noise. So what we want to show is that the part that varies because of the control and treatment is larger than the part of the noise. So that is the message here. You don't have to show that this is true. You can believe me that this is true. But what is important is that in all this variation that we see, a part of it is because people are different, and that is the noise. And a part of it is because you are in different groups. And that is what we want to show, that the difference between groups is larger than the difference between people. if the treatment is not effective, then this group would go down, this group would go up, and then the differences between the control and the treatment are not significantly different from the variations that we see from the noise. This is all you are doing when you are doing an hypothesis test. You want to show that the differences are caused by the control and treatment rather than being caused by variability between people. The name ANOVA, analysis of variance, is exactly that. Okay, so with that, we will construct an ANOVA table that, if you have used ANOVA, you may be familiar with it. And again, don't pay attention to the details, but there is some important columns here. So the first column is how much variability we are observing. And we have done here this decomposition. So we have a total variation, we have a variation that depends on the group, and we have a variation that depends on the people, on the variability of people, that we will call noise or residuals. So this is the first column, how much variability you are having here. The second column counts how many parameters you need to estimate those. Okay, let's look at this. How many? So these are called degrees of freedom, which is a kind of funny word that the statisticians like. So degrees of freedom, you may think of them as coins. So every time you get a measurement, you get a coin. So if you measure 1,000 people, you get 1,000 coins, but you have to estimate parameters. You have to estimate what is the overall mean. So the overall mean, you have to pay one parameter for that. You have to estimate what is the contribution of the being in the control. You have to pay another coin for that. You have to estimate the one of the treatment, but actually that comes for free because you have this constraint. So you have the constraint that the addition of these two has to be 0. So one, you know, one of them, the other one comes for free. So you don't have to pay a coin for that. So if you have two groups, you have to pay only one coin to estimate those parameters. So you have paid one for the mean, one for the control group. So you have spent 2 coins, and then you have 998 coins left. Okay, so that is what is gathered here. How many coins you are paying for each one of the things. So there were 1,000. Let us see it with an example. So let's say that in this example of the placebo and the treatment for the hypertension, this was the total variability that you were seeing, and only 256 were coming from the treatments. The other 13,000 is coming from the residuals. Is variability you cannot explain. But you had 1,000 coins. You paid 1 for the mean, so there were 999 left. You paid another 1 for the treatment, and then there are 998 for the residuals. So this number may seem impressive, but impressive especially when compared to the variability explained by the treatments. But all this variability has been explained by almost 1,000 parameters, while this variability has been explained by only one parameter. So the right comparison is not at the level of variability, but variability per parameter. So when you divide by the number of parameters that you have used to explain all this variability, it turns out that the treatments explain 256, and that is 256 divided by 1, and this 13,000 divided by almost 1,000 is 13. So a treatment, a single parameter of the treatment, explains much more than a single parameter of the residuals, and that is the comparison you are doing. This F is the ratio between these two. So a parameter of the treatments is explaining almost 20 times more than a parameter of the residuals. And that is based on this number is where you decide whether this is significant or not. You can compute from this number, you can compute the p-value, and this p-value will be extremely small. So when you are doing this experiment, you are comparing these, what you are trying to see is whether this parameter, that is the difference between these two groups, explains much more variability than each one of the individual residuals of each one of these people. And this is what we have succeeded to show here. Okay, so let's keep this number 18.87 in mind, because it will reappear later. Okay, so I have explained it with two groups, but this can be generalized to n groups. When you are doing a one-way ANOVA, that is what you are doing. So comparing all the groups and then seeing if the differences between groups are significantly above the level of noise. Actually, this F is a signal to noise ratio. Okay, now let's complicate it a bit more and let's introduce blocks. Okay, we are measuring blood pressure. It might be that constitutively part of the blood pressure variability that I see is explained not because people are different, but for some other reasons that I can identify. So for instance, males and females, they have different blood pressures, or young and old people, they also have different blood pressures. So what I can do is I take all the samples that I plan to study, I divide them into male and females. I don't need to have the same number of males and females, it doesn't matter. And then the males you divide into young and old, and the same for the females. And then at this point, you have young males. At this point, you have old males, young females and old females. So at these points, you have rather homogeneous groups, and those are the groups that you randomize. Now within an homogeneous group, I randomize to a control and treatment. So the variability, if all these variables, sex, age, they make a difference, by constructing homogeneous groups and then randomizing, I will be able to attribute part of the variability to the age, to the sex, or to whatever block I have designed. So the idea is, if you think that you have that there are variables that could be affecting my variability, then I should construct homogeneous groups of individuals with respect to these blocks, and then these homogeneous groups are the ones that I randomize. Okay, and here I have modified my observation model so that now I have an overall mean plus something that depends on your block, plus something that depends on your treatment, plus something that depends on the specific person. And now in my ANOVA table, there will be a new line. This new line will account for the variability explained by the blocks. So for instance, in this example of blood pressure, I have only one block that is gender, and then this gender explains 1500ths of the total variability with just a single degree of freedom. So, and this 1500ths is taken out from the variability from the residuals. So let's look at the numbers again. So this total variation is exactly the same total variation that we had in the previous experiment. So if we go back to here, it is exactly the same total variation. Numbers I have collected are exactly the same. But now part of this variability is explained by gender. And this gender variability is taken out from the residuals. The residuals was the noise, was the part of the variability I could not explain. But now I have another variable that helps me to explain variability. So all this explained variability is taken out. And the treatments explain exactly the same variability as before. The treatment hasn't changed. So now there is no free lunch, you have to pay. And how much? I have to pay just 1 coin for estimating the contribution of sex. But now I see that sex is actually the variable that explains the most variability. it explains almost 100 times more than the residuals. The treatments still explain the same amount of variability, but now instead of being only 18 times larger, it is 21 times larger, because now each one of these residual parameters is explaining much less. Before it was 13, now it is only 12, because part of the variability that I could not explain before, now I can explain with the blocks. So I find this, so if the treatment is has a weak effect, by explaining part of the variability with some other variable, may the weak effect, I may be able to show that it is significant. So explaining variabilities with as much things as possible is actually good to show that your treatments are effective or not. And also this experiment is also very revealing, because it means that to explain the variability caused by sex, I only need one coin, only 1 degree of freedom. So if you, there is always this debate, if I should use animals of both sexes, and if I have to do, should I double the number of animals? And actually it is not double. With just 1 more animal, or 2 if you want to make the groups equally sized. So with just 2 animals, I can divide them into males and females and study the effect of sex. So you don't have to double the number of animals for that. What you need is that the residuals have enough number of degrees of freedom, and enough, typically is somewhere between 10 and 20. So here we are overkilling, we are over designing our example, our experiment, so that we have many more samples than required to make this test. So yeah, that is why I said at the beginning that experiment design and sample size, they are related, but that is not, one is not exactly the same as the other. But experiment design already tells you, okay, maybe you have too many samples for detecting medium-size effects. Okay, so which are clear variables to block? So if you have liters typically they have significant differences between them. So liter is something that you want to put at this level. So you may want to randomize within the liter. You may also want to to block age, sex. The researcher doing the experiment, not every researchers work in the same way. So if all the controls are done by a person and all the treatments are done by a different person, maybe the differences are not because control are treatment, but because of the person who has done the experiment. So researchers are also typically blocked. The week of the experiment, maybe this week there's a problem with the batch of chemicals that we are using, and then the differences are not between control and treatment, but because of this difference in the batch of chemicals. So the week, within the week, we should again randomize and have controls and treatments. And there are people blocking also the position in the shelves and the rooms in the animal house, and there are many other things that you can also try to block if you think that they can have an impact on your measurements. And then your designs should look like this. So you have blocks, and for instance, here it was an experiment with 2 kinds of tumors. So we have females old with tumor 1 and females old with tumor 2, and females young with tumor 1, and so on. I'm cutting the design, but we have males and females, and the design is longer. And then within each one of these homogeneous groups, you randomize. So we have 3 treatments here. We have treatments A, B, and C, and we randomize, them with adjuvant and no adjuvant, and then you randomize the combinations too. And these groups don't need to be of the same size. So you see, for instance, here with tumor 1, there are more than with tumor 2. And the number of treatments, they don't need to be either the same. So if they are the same, if all the blocks have the same size and all the number of treatments, they have the same number of treatments for each one of the blocks, then that design is said to be balanced. And balancing is good. So I don't mean that you have to design in this way, but imbalancing is not terrible either. So there are mathematical ways of dealing with imbalance. But they should look like this. So you should have homogeneous blocks, and within the blocks you randomize, and you randomize with all the treatments and all the possible combinations of the treatments that you can think of. So let us go to the next kind of designs that are factorial designs. Okay, so you can deal with almost any experiment in a one-way fashion. So for instance, let's say that you are studying whatever outcome from your animals, I will call it Y, and we have 6 animals per group, and we have 4 groups. We have young males, young females, old males, old females. And then whatever you're measuring would be an overall mean plus something that depends on your group plus something that depends on that animal. Here I'm plotting the mean of the groups. So for instance, let's say that the overall mean is 5, and then the first group, the mean is 7. In the second group, the mean is 5, 5, and 3. So what are the effects of each one of the groups? So the overall mean is 5, but in this group you observe 7, then the difference is 2. So this 2 is this difference that we had at the beginning. So we have an overall a mean of 5, and then the mean of this group is 7. So this difference is 2. And then for the other groups, what we have is something similar. So we have a difference of 0, a difference of 0, and a difference of -2. And note that the sum of all this again is 0. Okay, I could do my one-way ANOVA analysis, and I would say, okay, my groups 1 and 4 are different, but the problem is that you cannot say why these 2 groups are different from the rest. Is it because of sex? Is it because of the age? A mixture of the 2? So you see that there are differences, but you cannot attribute to each one of the important variables there. So that is where two-way ANOVA comes in. So this was our previous design. Now we have another design. This is that takes into account the 2 factors. So we have the age and the sex. So now my observations will be an overall mean plus something that depends on the age, plus something that depends on the sex, plus something that depends on the specific animal. And here, for instance, now I can decompose. So for instance, I take the average of all the young animals. So the average of all young animals is 6, and the difference between 6 and the overall mean is 5. So that means that the effect of being young is +1, and the effect of being old is -1. And I can do the same for the females. So now I can explain this 7. So this 7 is an overall mean of 5 +1 because you are young, +1 because you are male. And this 3 is an overall mean of 5 -1 because you are old, -1 because you are female. So now I can see that these 2 groups are different from the overall mean, and I can explain why. So you get a positive effect because you are male, and you have a positive effect because you are young, and the opposite for females and old. So now by analyzing in a two-way ANOVA way, you can attribute which is the variability explained by each one of the factors. So now you would have we don't have it here, but you would have an ANOVA table like this one, and you would have one entry for sex, another entry for age, another entry for the receiver, and you know how much variability is explained by each one of these factors. And let's give another example. This is the same example, but now we are representing the data. So we have, for instance, I can put here male, females, and young, old, and then we see that if you are young, this is the change that you see when you go from male to females, and if you are old, the same, and the same happens. This is with male, female, and here it is. The axis is young, old, and what you see is that these lines are parallel. So parallel lines is a indication that the differences are caused simply by this sex or age, and only by those. And only by those are called main effects. Okay, here is another example. Now I have changed the data. So we observe 6, 6, 4, 4, and we can make the same decomposition as before. So what is the contribution of being young, being old, being male, being female? So now we see that there is no difference between male and females, but there is a difference in age. And then when we make these plots, we see that the young and old animals, they have a difference between them. So there is a gap between these two lines. And between males and females, we don't see actually the other one because it is under the one we have represented. So male and females have collapsed into the same line. So for this example, we would say, okay, there is a difference in age, but there is no difference in sex. And let's say that this is a different experiment, and now my observations are 6, 4, 4, 6. And now when I try to do this decomposition, what I see is that the average of young animals is 6. Sorry, is 5. There is a mistake here in the slide. So it is 5, and all the average of all animals is also 5, and the same for males and females. So it seems that there are no differences with respect to overall mean when I take only the main effects. But so I cannot explain this 6 because my model, what explains is, okay, what we observe is an overall mean that is 5 plus something that depends on your age, but the difference of age is 0, plus something that depends on your sex, and the sex again doesn't contribute to this. So I'm puzzled now. I cannot reproduce my data. If you make these plots, the same plots that we were doing before, so for instance, let's go for one of them. So we have males. So let's have young animals. So young animals, males get 6, females get 4. So we have this line for young animals, we have this line for old animals, and the same for males and females. And what we observe is that these lines are not parallel anymore. So before, in our previous examples, the lines were parallel or coincident. So we have parallel lines, parallel or coincident, but now they cross each other. So this crossing is calling for an extension of the model. So it might be that the age and sex interact with each other. So there are differences that depends on, so depending on whether you are young, then male and females behave differently if you are young or you are old. And the same for the age and sex. So males behave differently depending on whether they are young or they are old. So these interactions, this extra behavior is called an interaction. And then you can modify your model and say, okay, what I observe is an overall mean plus something that depends on the age, plus something that depends on the sex. These two age alone and sex alone. So these were the main effects, plus something that depends on the interaction between the two. So something that depends, because males, young males and old males behave differently. And now with this extra term, now I can explain my data. So I was observing 6446, and this 6 is explained as 5 because it is the overall mean, plus 0 because age alone is not making a difference, sex alone is not making a difference either. But now the interaction of age and sex is doing a difference. So young males behave differently and have a positive impact, while young females have a negative, and old males negative and old females positive. So now by extending my model, I can explain the data that I observed. And again, interactions will be another line in my ANOVA table. So, and I will have a line for the main effects of the first factor, the main effects of the second factor, the interactions between both factors. And these interactions are very cheap. So we said before, if you have two levels, so male and females, so you have two levels for that factor, you only have to spend 1 degree of freedom. In general, you have to pay p-1. If you have n p levels, you have to pay p-1 degrees of freedom. Interactions are very cheap. You only have to pay p-1 times q-1. Let's see an example. So let's say that you are interested in testing what is the water uptake by amphibia. So you have two species of amphibia, let's call them frogs and toads. And you want to see if this amphibia, when you inject them a mammalian water balance, this is a very different source of the hormone. So these are amphibia. We are injecting something from mammals, and amphibia mammals are relatively far evolutionarily. Okay, so let's see if this hormone has an effect on amphibia. And maybe because my experiment, I will inject the hormone or not, the vehicle, and then I will put the animal in water for half an hour. I will wait it before putting it in water and after putting it after being in water, and I will measure the difference. So if the hormone has an effect, then those receiving the hormone will behave differently from those not receiving the hormone. But maybe the amount of water they receive depends on whether the animal had been in water before doing the experiment or not. So if that is the case, then this factor will also have an influence, this whether they were in water before doing the experiment. Okay, so you do your experiment. What is your model now? Your model is that your observations is an overall mean plus something that depends on the species plus something that depends on whether they were in water before or not, plus something that depends on your treatment. This is the one that you are really interested in, plus possible interactions between a species and being in water before or not, a species and hormone, and moisture and hormone. And we will not consider, we could here in the equation, we don't have the triple interactions, but you can include them. When you analyze your ANOVA table, you see that a species you had 2, so you have to pay only 1 degree of freedom. The same for the moisture, the same for the hormone. We had 8 combinations in total. So if you count how many ways you can combine frogs, toads, dry or wet before, and hormone, not hormone, there are 8 combinations. We have a couple of individuals for each one of the combinations. So we had in total 16 animals. We have to pay 1 degree of freedom for the overall mean. So we have 15 degrees of freedom left. And one of them is spent in the species, one of them in moisture, one of them in hormone. And here you have the interactions. The interactions are extremely cheap. they are only 1 times 1, 1 times 1 all the time. So they are very cheap, and the remaining degrees of freedom stay for the residuals or the errors. So now you compare the amount of variability explained by each one of these factors to the amount that you have not been able to explain that are the errors. So for instance, this species anormone, it is significant because it is explaining a lot, while this one, species and moisture, it is not significant. So here, this is explaining 39 compared to 34, and while this species anormone is explaining 165 compared to 34. So in this comparison of signal to noise ratio, we see that the species anormone, there is an interaction. Not all the species respond equally to the hormone. That is a very interesting result. But for being able to analyze the data in this way, you have to say how you will analyze your data. What is your equation model about how your data is generated? And when you get into the analysis programs, somehow you see these questions, sometimes very explicitly, some other times not so explicitly. And here is another thought about this factor analysis. So for instance, let's say that we have 24 animals available for this experiment of frogs and toads and so on. And the general wisdom in labs is that you should change only one factor at a time and compare those two conditions. So for instance, we can compare frogs. I want to see if the species make a change. So I will compare a group of frogs dry with no hormone to toads dry with no hormones. And I will have 4 animals in each one of the groups. And then if I see differences, these differences are caused because of the species. And then being wet or dry before doing the experiment, and 4 animals each, and then hormone, not hormone. So this would be a possible way of designing the experiment. Another way would be this one. Okay, so if you look at this design, this group is the control group, has been used 3 times. And this control group, altogether, it has 12 animals in total. And the other 12 animals are distributed in this, checking whether the species being wet or dry before the experiment of the hormone makes a difference. You could have, okay, this group, the control group, is using 12 animals. Okay, I will use only 6, and the other 6 remaining I will distribute in these other groups. So now in total I still have 24 animals, but now the structure of the experiment is different. The factorial design that makes all possible combinations, that are 8 combinations, is using 3 animals in each one of the combinations. And again, the total size of the experiment is 24. But you see that the 3 experiments are very different. Turns out that the most powerful experiment is this one. So whenever you want to make any one of these comparisons, the species is making a difference, being dry or wet is making a difference, the hormone is making a difference. All those comparisons, the most powerful ones, powerful in terms of capacity to tell you if there is a difference or not, it is given by the factorial design. And here is another example. So let's say that you're interested in the survival of Salmonella of a bacteria, and you have 3 possible factors that you can change. So you have the 3 possible concentrations of sorbic acid, 6 possible levels of water activity, and 3 possible levels of pH. And then you will measure how much, what is the density, the optical density of some cultures. And okay, so if you count how many experiments combinations I have. You have 54 possible treatment, 54 possible combinations of sorbic acid with water activity, with pH, and you would have to do 54 experiments or mini experiments. If you use 2 replicates of each one of these combinations, and you count how many degrees of freedom you have for the errors, you have an enormous account. It is kind of the same as we had before with the 1,000 people for the treatment or control in the hypertension example. So you have so many that you are overkilling. So can I use just one replicate? And the answer is yes. You have to sacrifice something. You have to sacrifice that. You count how many degrees of freedom you have for the water activity, for the sorbic acid. Here we have all the possibilities. And you have to sacrifice something. What you are sacrificing with just one replicate is that the three-way interactions, so the interaction, this particular activity of water with this particular level of sorbic acid, with this particular pH is particularly good or particularly bad. So you're assuming that those are errors. You cannot estimate those parameters, but you have 20 of those. And then if you sacrifice estimating these parameters, then all those degrees of freedom become available for the errors. And now you can show whether these main factors or these two-way interactions are significant or not, with only one replicate per combination. And you can bring this further. So for instance, let's say that you are interested in how cells grow in a bioreactor, and then you have identified 7 possible variables that may affect. So you have identified temperature, humidity, pH, concentration of oxygen, many concentrations. And for each one of these variables, you have 2 possible values. So in total, there are 128 combinations. Do I need to do all combinations? And now we know the trick. The answer is no, because you can sacrifice high order interactions, give them to the residuals, and then with many less combinations. So for instance, with only 64, you can show whether the main effects are important and whether the second order are important, but you don't care the third order interactions, the fourth order interactions. So you don't have to do all possible combinations. So these factor designs, they allow you to do experiments with only one replicate per combination, or not even doing all combinations. This is an incomplete or an imbalanced design that we mentioned before. So the message of these factorial designs would be hold all factor constant except those whose effects you are investigating. So those that you are trying to do research, you should vary them as much as you can. So not do just one factor at a time, but if you are analyzing these 3 factors, analyze them, combine them as much as they can, and then they will give you a lot of power. Okay, regression design. We are familiar with this kind of experiments where we have, for instance, a response, and we are analyzing different doses, and then males and females may respond differently. So now in our two-way ANOVA, we would have a contribution from the dose, a contribution from the sex, and a contribution of the interactions. If you count number of degrees of freedom, you have 19 degrees of freedom, which is a lot. So you need many animals to estimate all these number of degrees of freedom and still have degrees of freedom available for the errors. Now you change your model. You say, no, I will do a regression model. So now it looks more complicated, but here, if you count how many parameters you have, you only have 5 parameters. So I don't have to estimate 19 parameters, but only 5. So I need fewer animals. And also because I know the shape of the curves, I don't know which exact curve I will have. I need the experiment for that, but I know the shape of the curve. Then I may distribute my samples, my doses, in such a way that I get the maximum information from the samples I will take. So the experimental design not only affects how many animals you have, but also how you should distribute your doses for that. And this is called a regression design. So you know what kind of functions you are trying to fit, and then you design your points accordingly to those kind of functions. So in conclusions, the goal of our research is to show that there is a difference with respect to some factor, typically the control and treatment. And to be statistically significant, this difference has to be above the level of noise. Experimental design helps controlling and identifying how much variability is caused by each one of these variables. You should always randomize at the level of blocks, so construct blocks that are as homogeneous as possible in terms of the blocking variables, and then there you randomize. And this would be the mantra that you should keep in mind. So control what you can, block what you cannot, but you can measure, and randomize the rest. So this would be a summary of this talk. And now I'm open for questions.
Thank you very much, Carlos. Thank you very much, Carlos, for the very good talk and very informative presentation. I think we have time for a question from the chat. If anyone would like to ask a question, you can press the button and raise your hand if you want. If you have a question, we don't have questions in the chat. There's one from Anne-Marie. So yes. Please unmute your microphone. Yeah.
I have a few questions actually, but I guess my most important question is like, because it's really interesting talk, and I'm learning a lot here now because our group hasn't really done a lot of randomization or stratification in the past. But I was wondering, because we cannot really control all of the variables, because you're breeding the mice and you just get kind of what you get. So you have a number of females and males, and they have a certain age. Like, it's not always possible to like perfectly divide that into blocks and have enough of the combinations. So how do you deal with that?
Yeah. So what you're saying is that you cannot have exactly the same number of females, males, old, young, and so on. But that is an imbalanced design, and it doesn't matter. So what you can have, you can separate males and females, young and old, whatever number you have. And once you have young males, those are the ones that you randomize. So let's say that you have only 4 young males. So 2 of them will go to control randomly, and 2 of them will go to treatment. And then you have 10 young females. 5 of them will go to the control, 5 of them will go to the treatment. And then the analysis will take care of this imbalance.
But I was just, we have sometimes like 4 treatments or 5 treatments. And then, we have like more young females and more old males or something. And it's not really possible to get.
You see here. Yeah. So for instance, here in this example, you see, we have many more old females with tumor 1, and only one of them is receiving treatment C. It is important that at least one receives it. Okay? But even if this group is not receiving treatment C, it is not a total disaster. So still it can be analyzed. So the more difficult you put it to the analysis, the worse for the power and so on. But it can be treated like that.
Can I have one more question?
Equal numbers.
I think you can have the last
question. If you have them, the better. But it is not.
Sure.
Yeah, Mari, go ahead. You can have.
Oh, okay. I was also wondering if you have a favorite tool for doing the randomization and the blocking. Like if there's a nice easy software to do that, and also for the analysis, because I usually do my analysis in Prism, but I don't think I can add all those variables.
Design Expert.
Sorry?
Carlos, are you there?
Yeah. So for this randomization and blocking, I am. Can you hear me? You can hear me?
I think so. It was the connection was a bit unstable, but we can hear you now.
Okay, good. So my favorite tool to do the blocking and the randomization is Design Expert, but unfortunately you need the license, and my institution we have, but I understand not everyone. And then that is what I use. And otherwise, I'm sure that in R there must be something, but I'm not aware of it.
Okay, thanks.
More questions?
You're muted.
Am I muted?
Oh, sorry,
No.
I was speaking here by myself. Anyway, so it's 2 o'clock now, so it's just time to leave it here. Please feel free to drop your questions, your final questions in the chat if you have one, very quickly, because we are going to close very soon. We just want to thank Carlos for sharing your time and knowledge and for the very nice presentation. Thank you very much. And thank you all for attending this webinar. And of course, thanks to the sponsors, the Kea Board of Research, the Kea Committee for Doctoral Education, SLAB, LAVA, Scandas, the Finnish Center of the 3 Rs, and the Fondazione Guido Bernardini.